Okay, so we finished the last video talking about positron emission, which is a nuclear reaction where the nucleus gives off something that's called a positron. Now, they named it that before they knew what the positron was. We now know it's a positive electron, so it's the antimatter, the anti-electron. And this usually happens after a nucleus has become unstable. So when we use a particle accelerator and speed a subatomic particle up to a high rate of speed and then collide it with a nucleus, lots of times then that subatomic particle gets absorbed by the nucleus is unstable, and that is when we will either the nucleus that is formed is unstable, and it can often then give off something that's called a positron, a positive electron. Okay, so positive beta particle, positive electron, so it's called positron emission or positive beta decay. And we call this artificial transmutation simply because we haven't detected it happening on its own. It happens as a result of us doing something to the nucleus to make it unstable. Okay, and sometimes when that subatomic particle is absorbed, a totally new nucleus is created, new element, not like different one than what we started with, and then that one is what's unstable and it emits the positron. Okay, the next type of artificial transmutation is called electron capture, or K capture. So again, this comes about as a result of us running an experiment that creates a nucleus that's unstable. Okay, so it's already absorbed that high speed proton or whatever it was, alpha particle that we were shooting at it, and then the nucleus is unstable. Electron capture usually occurs when the nucleus has too many protons relative to the number of neutrons. Okay, so too many protons compared to the number of neutrons, just like the positron emission. Now, I had told you a while ago when we were doing the models of the atom that we would come back to K capture in the nuclear unit. Because if you remember when we were doing the models of the atom and we were in quantum, we were saying that they were saying let n equals 1 shell be called K, and n equals 2 be called L, and n equals 3 be called M. And I said the only time I've ever seen the letters being used for that n shell, the n number, is in this exact spot. K capture means that, or electron capture means that it's pulling an electron from the n equals 1 level. So the nucleus has too many protons relative to the number of neutrons. And so what it does is it grabs an electron and pulls it in, right? And so when it pulls that electron in, a proton inside the nucleus, and because it's inside the nucleus, I'm writing it as a P instead of an H, right? The 1,1H is when it gets emitted. So it pulls an electron in, and so then the electron and the proton inside the nucleus interact, and if you add this up, you'll see you get a 1, 0, which is a neutron. Okay, so in a K capture, it pulls the electron in, and the electron and the proton join together and become a neutron. So the atomic number is going to decrease by 1, but the mass number is going to stay the same. Okay? Now, when this happens, the nucleus is in a high state of energy. It's like really excited. It's just pulled in an electron. Like, this is a major coup. And so usually after an electron capture, a gamma ray is given off. So an example of this would be potassium 40. Okay? Potassium 40 will pull in a beta particle or an electron, and it will become 4018. And if you look 18 up in the periodic table, it's argon, and then a gamma ray. Okay, and remember, gamma is a fish standing on its head, and it's 0, 0. So electron capture, positron emission, types of artificial transmutation, things that we've only discovered thanks to our particle accelerators and our particle detectors. We're going to move on now to a third type of artificial transmutation. It's probably the most famous. It's called nuclear fission. We will also do nuclear fusion, but nuclear fission is when something splits apart. Fusion is when it's brought together. Fission is when it splits apart. Now, you might think, okay, but we've looked at different nuclear reactions where like it gave off an alpha particle or whatever, but that's just radioactive decay. Fission is when you have a really heavy nuclei and it splits into two almost equal parts. So not like an alpha particle and then, potassium. Like that's not two equal parts. So it's when you have a really large nucleus of an atom or an element that has a high atomic number, and it splits into two nearly equal pieces. It doesn't have to be totally equal, but it's not like one ends up with 40 nucleons and the other ends up with 3. Okay, it's more equal than that. Okay, it often occurs as a result of absorbing a neutron or sometimes a high energy gamma particle. Now, not every element can undergo nuclear fusion. There are fission. Okay, there's only really a few of them. They have to have a high atomic number. So the lower atomic numbers, this does not work for. The two most common are uranium-235, and uranium is 92, and plutonium, and we've talked about both of these, seen them both in nuclear reactions. Plutonium-239, and plutonium is, I want to say 94, but I better check it before I say that. It is 94. 94. These are the two most common elements or isotopes of elements that are used in nuclear fission. Now, when these break apart, and there's several different, there's not like a one set thing that always happens. There's several different possible nuclear reactions here. But when they break apart, the two parts you get are called fission fragments. And those fission fragments usually have too many neutrons compared to their number of protons, and so then they give off 1 or 2 neutrons right away. They also give off a huge amount of energy. Remember not that long ago, yesterday, today, anyway, there was a question, I think it was last night's homework, or the lesson before this homework, where you had to figure out the amount of binding energy per nucleon. And what we discovered was the bigger the nucleus, the bigger the binding energy per nucleon. So uranium-235 is going to have a lot of binding energy per nucleon. But when it breaks apart into two smaller particles, the amount of binding energy each of those needs is less. And so there will be excess energy left over. And that excess energy is what we use either for power or to blow up a country. Okay, so for 235, two of the different possible nuclear reactions that could occur. So it's uranium-235, and you have to shoot in something to start it. So I think the other day I said, you'll always know if it's spontaneous decay if there's nothing written on this side, if there's no plus. But as soon as you see a plus, then you know we're doing something to it to make it decay. So uranium-235 gets shot with neutrons. It takes those neutrons in, so it becomes 236,